Okay, so we're going to take a look at section 3.3. The title of the section in the book is the factor theorem. It really covers long division, remainder theorem, and factor theorem. It covers all three of those things. So just a couple reminders about what it means for a number to be a root or to be a zero. Okay. If a number is a root or a zero, it means that it is the answer to the equation when you set it equal to 0. So if I had something like this, let's say 2x minus 6. What number could you plug in for x there? And it would be the solution when you set it equal to 0. Yeah?
3.
3. So 3 is the root of that equation. Okay? It's the number that when you plug it in, the solution is equal to 0. That's a root. So this second statement has an abbreviation in the middle you might not have seen before. IFF means if and only if. And from geometry, if and only if is a statement that you can read forwards and backwards. Okay? That's called the original and the converse. And they're true. It's true both ways. So if a number is a root, then when you plug it into the equation, you get 0. If a number is a root, then when you plug it into the equation, you get 0. Or the other way I can read it is, if I have a number that I plug into an equation and get 0, then that number that I plugged in is a root. So that's a statement that's true forwards and backwards. So kind of using our example here, where positive 3 is the root. 3, if 3 is a root, then that means it is a solution to when you set the equation equal to 0. Yes. Or I can say, when I plug 3 in for f, because I get 0, then that means the number that I plugged in, 3, is a root. Right. So any questions on reading that statement either way? Okay. So let's look at an example with a number. So we're going to do some long division. But I'm going to start out just by using a number and kind of get you thinking about the process we're going to do. So let's say that I want you to factor the number 12. That means I want you to write it as something times something. And I'm telling you one of the numbers I want you to use is 3. So I want you to factor the number 12. And I'm giving you a hint that 3 is one of the factors. That means 3 times something equals 12. How would you solve for the something? Yeah.
Divide 12 by 3.
Divide 12 by 3. Yeah. Divide each side by 3, and what would you get?
4.
4. Exactly. So now that we know the something, we can factor the number 12 as 3 times 4. Okay, but to figure out 4, we had to use the factor that we already knew and divide it into what we were trying to factor. Now, notice when you divided 3 into 12, I told you 3 was a factor. When you divide 3 into 12, what do you get for a remainder if you were to do long division? Yep. 0. Anytime you divide by something that is a factor, you always get a remainder of 0. So that's a quick way to tell if something is a factor. If you do division and you do not get a remainder, then that means it is a factor. If you divide by something and you get a remainder, then that means it's not a factor. So you need to get a remainder of 0 for something to be a factor. So besides doing long division, we're going to want a quicker way to figure out the remainder to something. Sometimes we'll want to know the quotient. But if all we want to know is is this a factor of that? If we can get a remainder really quick, that'll tell me the answer. So what we're going to do is we're going to use long division. Long division is going to help us to do factoring. Just like right here, we didn't really have to use long division, we just did regular division. 12 divided by 3 and it gave us 4. Well, with polynomials, the division's a little more complex. Okay, so we're going to have to use long division. And that helps us to factor something. So if you had something like x squared, let's say, plus 5x, plus, let's do 6. Looking at that quickly, you might not be able to tell the two numbers you can plug in for x to get 0. But if you write it like this, you should be able to look at that extremely quickly and know the two numbers are -2 and -3. So that's why we will factor polynomials. Gives us a quick way to figure out the numbers we have to plug in to get 0 as the answer. A quick way to find the roots. Any question what the advantage is to the factoring? Okay. So that process that we used when we figured out 12 times, what was it, 3 times 4 is 12. We can do that same process with a polynomial. So the division, a little bit more complicated. Okay, we're going to have to do it as long division. But what I'll do is I'm going to give you the steps, and I'm going to show you a problem kind of at the same time. So put that up. So I'm going to have steps on the left, and then I'm going to do an example on the right. So the example we're going to do is we're going to try to divide x minus 3 into x cubed minus 8x plus 3. Well, the first step is we got to make sure that the dividend, which is the thing I just circled, is set up right. Okay, that's not set up right. If you are missing any terms, you need to fill in zeros. Okay, and what do I mean by missing? Well, if your highest exponent in the dividend is a 3, then you need to have every x term that has an exponent from 3 all the way down to the constant. X cubed, x squared, x to the first, then your constant. So looking at this, am I missing any of the x terms? Yeah?
Missing x to the second.
Right, I'm missing x to the second, and that's going to be a problem because we're going to get x to the second power as we do this. We need a spot to put those. We need a column. So let's make a column, and we'll use 0x to the second as a just like a placeholder. Okay, so now we've got x cubed. Doesn't really matter if you do plus 0x squared or minus 0x squared. It's just a placeholder. So 0x squared minus 8x plus 3. Okay, now we're ready to do division. Okay, first step. You're going to take the first term of the divisor. That's the thing on the outside. And you're going to divide it into the first term of the dividend. That's the thing on the inside. So for now, you're not doing anything with the minus 3. That comes up in the next step. Okay, so take the first term on the outside, which is x, and divide it into the first term on the inside. Right. What's x cubed divided by x? Yeah.
X squared.
That's going to be x squared. Doesn't matter where you put that. You just put it up above the line anywhere you want. It doesn't have to line up with anything. So that's the first step. Next step. Take your answer from step 2 And we're going to multiply that back out to each term in the divisor. It's kind of like a distributive property. Okay, so let's multiply x squared back out. What's x squared times x? Yeah, x cubed. And what's x squared times negative 3? Yeah, negative 3x squared. Okay, so that's the third step. Any questions on how I multiplied that back out? Yeah.
Can you show it again real quick?
So x squared times x is x cubed. And then x squared times negative 3 is negative 3x squared. So that's the two things that we multiplied and put them in the right columns. Cubed is in the first column, squared is in the second. Okay, now we are going to subtract those columns from step 3. So what I do is I do it like this. That's how I write it. Okay, we're going to subtract everything we just wrote down. What's x cubed minus x cubed? 0. That's gone. Okay, when you do line division, there's a column that should always cancel out at every step. If something doesn't cancel, there's a mistake. How about 0x squared minus 3x squared? Yeah, 3x squared. Okay, and that's step 4. So what do you think we do next? We did the divide, multiply, subtract. What do you think my next step is so I can do this process again?
You bring down the rest.
Yeah, we're going to bring down the next term. I just bring down one at a time. So the next term is negative 8x. And you keep repeating this process until one of two things happen. Either this number is smaller than that number. So I had x to the first on the outside. And originally it was an x cubed on the inside. Now it's an x squared. So we need to keep going until the number on the inside is smaller. Or everything on the inside disappears and we have a remainder of 0. Sorry about that. I think the and repeat is right there. So bring down the next term and repeat that until you don't have a remainder, or the exponent on your remainder is smaller than the exponent on the divisor. Okay, so we need to keep going because our exponent is a 2 on the inside and a 1 on the outside. Okay, so now we're going to divide x into 3x squared. What's 3x squared divided by x? Yeah. Yep, so we're going to do plus 3x. Multiply that back out. 3x squared minus 9x. And now once I have my columns, what do I do with the numbers in each column? Yep. Subtract. Good. 3x squared, take away 3x squared. That's gone. What's negative 8x minus negative 9x? Yeah.
X.
Yep, 1x. What's the exponent on that x? 1. So the exponent is a 1 here. It's a 1 on the outside. I need to keep going until it's smaller. Okay, so bring down my next term. Okay, and we do it one more time. Divide x into x. What's x divided by x? Charles? 1. And if all you wanted was the quotient, you're done. X squared plus 3x plus 1. But generally, when they say divide, they want quotient and remainder. So multiply the 1 back out. 1 times negative 3. And Noah, what am I going to do with my columns?
Subtract.
Subtract them. X minus x is gone. And what do I end up with for a remainder? Yeah, 6. There's my quotient. I'm sorry, there's my quotient at the top. 6 is my remainder. Okay, so there's a couple ways you can write your answer. One way is like this. The quotient is x squared plus 3x plus 1. And the remainder is 6. Any question on writing it that way? Okay, the second way you can write it is the same way you probably learned how to do it when you learn long division with numbers. So let's look at an example, and I'll go right back to that. Let's take 17. And let's divide 3 into 17. What's the quotient and remainder when you divide 3 into 17? 5 remainder 2. So one way you can write your answer when you have a quotient and remainder is quotient plus remainder over the original divisor. My quotient was 5. My remainder is 2. And my divisor was 3. In other words, that's 5 2/3 when you take 3 and divide it into 17. We're going to do the same thing with a polynomial. Quotient plus remainder over divisor. Okay, so my other way I can write the answer is quotient plus my remainder over my original divisor, x minus 3. So that is another way you can write your answer. And the advantage to the second way is I can check it. If I type in what's in this box, that's what I think the answer is. I can put that in the calculator. I can put the original problem in the calculator and see if when I actually do the original problem out and graph it, do those two things look the same? So let's start with the original problem. It was x cubed minus 8x plus 3. You don't need to fill in zeros when you type it in. Okay, that's just for us, and that's more of a visual. Minus 8x plus 3 divided by x minus 3. Okay, so that was the original problem. Now let's put what we think the answer is. It's x squared plus 3x plus 1. So x squared plus 3x plus 1 plus, let's do it, how do I want to do this? 6 divided by x minus 3. Just want to make sure order of operations, it doesn't try to like add 1 and 6 first to get 7. But I don't think it will because of the way I typed it in. All right, so let's graph the original problem and let's graph our answer. Okay, so there's the original. And here's our answer in red. How do the two graphs compare? How do they compare? Yeah.
The same.
Yeah, they look the same. Just because they look the same, that doesn't really prove anything, but it highly suggests what I have here is the correct answer. And because we did algebra to get that answer, that's how I know it is correct. It is correct. All right, any question on that? All right, let's try this one. Okay, so this time I have already filled in what was missing. So they didn't give you a squared term and they didn't give you a linear term. What's the degree on the outside? What's the degree of my divisor?
2.
2. So my degree on my remainder has to be smaller than that. It always has to be smaller than that number. Okay. All right. Without me kind of walking you through step by step, can anyone just tell me what the first step is? Yeah.
It would be 2x to the 4th divided by 2x to the 2nd.
Yep, 2x to the 4th divided by 2x to the 2nd. And how much is that?
X squared.
Yep, x squared. Okay, Jordan, what do I do with that x squared? Yep, multiply it back out. And what do you get when you multiply it back out? X cubed plus x squared. Okay, so we multiply it back out. Aiden, once I multiply it back out, what am I going to do with each of these columns?
Subtract.
Yeah.
I was actually going to say what he was going to say, you subtract them.
Yeah, you're going to subtract them. So we subtract them. 2x to the 4th minus 2x to the 4th is gone. And what am I left with when I do that subtraction at this step? Yeah, Matt?
You subtract them.
Yep, we subtract them. And what do I get?
You would get 2x to the 3rd for the second of it, I think. And then you would get minus x squared.
Okay, minus x squared, that's good. Can you tell me that first one again?
2x. Negative 2x.
Yeah, negative 1 minus 1.
Negative 2x to the cube. Oh, I was saying squared. I meant to the 3rd.
So negative 2x cubed.
Yep.
Okay. Degree on the inside is still bigger than the outside, so we got to go again. Bring down the 0x. Again, that's more of just like a placeholder. And what's negative 2x cubed divided by 2x squared? Colin?
Negative x.
Yeah, you're just going to get negative x. And can you tell me what you get when you distribute that back out?
You get negative 2x to the 3rd. Take away x squared minus 1x.
Yep. Okay, subtract all of that. And what happens when I subtract here? What happens to my first column? Aiden?
Cancel.
It cancels out. What happens to my second column? Yeah.
It also cancels out?
It also cancels out. That doesn't always happen, but when it does, it's nice because we just got two things to cancel. And what do I get for the last column? That does not cancel. Yeah, we get x. And what's the degree or what's the exponent of x? 1, is that smaller than the original degree of the outside? Yeah, so we're done now. So now we just have to interpret what our answer is. Okay. Emma, what's my quotient? Yep, perfect. X squared minus x. And Peyton, what's my remainder? X minus 2. You could write that answer in the other format I showed you as well if you wanted to check it. But that's your quotient and remainder. Again, notice remainder has a degree of 1, which is smaller than the divisor, which had a degree of 2. Any question on that? Okay. So how do you check your answer when you do long division? So if you had a problem like this, and you want to check that answer, if you take your quotient and remainder, there's a way you can check it. If you take the quotient and you add, no, one thing first. Take your quotient and you multiply by the divisor and add your remainder. That's how you learn to check an answer when you do long division. Your quotient is 5. What you were dividing by was 3. And your remainder was 2. If when you do that calculation, it comes out to the number that was under the division sign, then you did it right. So quotient times divisor plus remainder should come out to the dividend. The dividend is also known as the numerator, and the divisor is known as the denominator. All right, so that's how you check your answer when you do long division. We're not going to check our answer with long division, but I'm going to show you how we can use this concept to help us figure something out a little faster. So this formula that I just wrote down, that's exactly the formula I just did on the other page. Except instead of writing the word quotient, I'm calling it Q of x, because the quotient will be a polynomial. R of x, that stands for remainder. F of x is the numerator, and h of x is my denominator. So if I do this same thing with, I'll do 17 and 3 again. If the numerator was 17 and the denominator was 3, when I divide them, the quotient is 5 and the remainder is 2. That means that the numerator should equal my divisor times my quotient plus my remainder. And it does. So any question on that formula right there? Okay. So remember, when you divide, and I've said this a few times, the degree of the remainder is always lower than the degree of the divisor. Or you get a remainder of 0, and then you're done. So if I had something in the top, that doesn't matter what. But I divide by something that looks like that. There would be a number in that box. The number doesn't matter. What's the degree of that? Yeah?
Can I fill this up?
Yeah. Do you know the degree?
1.
Yeah, good job. It's degree 1. So the degree of this is 1. When I do this division out and I get my remainder has to have a degree that's lower than that. What's lower than degree 1? Yeah?
0.
Degree 0. And what is a degree 0 polynomial? Like degree 2 is quadratic, degree 1 is linear. What's degree 0? Yeah? Yeah, it would just be a constant. So that's an important idea to remember. If you divide by something that's degree 1, you will get a remainder that is degree 0. Other words you can use for those is if you divide by something linear, you will get a constant for the answer in the remainder. And I showed you guys an example of that in the first problem we did. We divided by something linear, and the remainder that we got was a constant. It was a degree 0. If you divide by something linear, there is a quick way to get the remainder. Okay, a lot quicker than doing out long division. I'm going to show you what that is. If you're dividing by something that is quadratic, no, there's no quick way that I'm going to teach you for how to get the remainder. You just have to do it out. So let's take this box that's very general, and let's make it more specific for the situation where you're always dividing by something that is linear. Okay, x minus some number. It could be x minus 5, x minus 6, it doesn't matter. Just x minus some number. Okay, so when you divide two polynomials, that's kind of the general way to write it. And that's how I did it up here. But now, instead of the bottom just being anything you want, I want the bottom to specifically be x minus a number. The bottom has to now be x minus a number for this next step. So remember the formula. Your numerator is equal to what you divided by times your quotient plus your remainder. So it's the same formula I wrote up above. But now the denominator is something very specific. It's x minus a number. So numerator equals denominator times the quotient plus your remainder. My goal is to figure out this remainder. If I could somehow make everything in this green box cancel out, then I would be left with some formula equals my remainder. I just have to figure out a way to make all the stuff in that green box disappear. And I can do that if I plug in a certain value for x. Does anybody see what value you could plug in for x? And if you did that, everything in this green box would disappear. Yeah?
6.
Yeah, plug in what?
6.
That's a capital C.
Oh. Oh, that's not bad.
Yeah.
C.
C, right. If you plug in C for x, this is what would happen. So if you plug in C for x, instead of saying f of x divided by h of x, we're going to say f of c equals, and replace everything that I'm circling with a c. And if you do that, what you end up with here is c minus c times q of c plus r. Now, q of c would mean you take your formula for the quotient and you plug c into it and see what you get. F of c means take your formula for the numerator, plug c into it, and see what you get. plugging c into the quotient doesn't matter. Because you're going to take this and multiply it by what? Yeah? 0. So by plugging in c into the formula that was in the top of your fraction, it causes all of this to cancel. And the only thing you're left with is the remainder. So what's in that box? That's called the remainder theorem. If you take the number that comes after the minus sign, what I just put a box around, and you plug that number into the top, what you're left with is the remainder. And the reason why is because this part cancels out, and r is the only thing that's left. Okay, but the remainder theorem only works if you're dividing by x minus a number. Anything you want in the top is fine. Anything. But the bottom has to be x minus a number. So yes, you might think that's a very specific situation. It is. But that situation comes up a lot. Okay? Dividing by x minus a number. So let's go back to the first problem we did. And let's find the remainder using this theorem and compare it to the remainder we got when we did long division. So remember, it's always the number that would be in this box, not the minus sign. What comes after the minus sign? That's the C. Right there. Okay, so looking at the first question. In this one, am I dividing by something that is x minus a number? Yeah. What is the number after the minus sign? It's a 3. So let's take that number, and the formula, go back here, the formula says to take that number and fill it into f. What is f? F is your numerator. So fill in that number into your numerator. Okay, so my numerator is x cubed minus 8x plus 3. And I'm going to fill in the number after the minus sign, which is a 3. So I get 3 cubed minus 8 times 3 plus 3. What's 3 cubed? Yeah.
9. No. 27.
27. And 8 times 3 is 24 plus 3. What's 27 minus 24? 3, and then plus 3? 6. So when I plug in 3 for x in the top, I get 6. What was the remainder when we did this problem? 6. If you divided by x minus 5 and you wanted to know the remainder, fill in a 5. If you divide by x minus 30, fill in 30. Okay, all you have to do is fill in the number for x and it gives you the remainder automatically. Let's try another one. So this one says find the remainder when you divide f of x by h of x. And then we're going to do g of x after. Start with f of x divided by h of x. All right, so first of all, if I do f of x over h of x, am I dividing by something that fits the pattern I said it needed to? What do you think? Yeah, Olivia?
Yeah, it does.
Yeah. H of x fits the pattern that it's supposed to for the remainder theorem. It's supposed to be x minus a number. Okay. So what, in h of x, what is the number that comes after the minus sign? Charles?
3.
Yeah, 3. So you're going to take the number after the minus sign, and you're going to fill that in for x in the numerator. And that'll give you the remainder. So it's 3 cubed minus 2 times 3 squared is 9, plus 3 minus 5. Okay, 3 squared gives me 27, minus 18, plus 3 minus 5. Noah, what's 27 minus 18?
9.
And then plus 3? And 12 minus 5? 7. So that is the remainder when you take f of x and divide by h of x. You get a remainder of 7. Okay, so now let's see if you remember what I said earlier on about remainders. When you try to divide that in, it does not go in evenly. I know that because I got a remainder of 7. That means that x minus 3 is not a what of f of x? Yeah? Factor. Perfect. It's not a factor. Yeah. If it was a factor, what would I have gotten a remainder of? Yeah.
0.
I would have gotten 0. But I didn't. So. All right. Let's do f of x divided by g of x. Okay. Are we dividing by something that fits the way it's written? Does it fit the pattern I said I needed to? To use the remainder theorem. Does g of x fit the pattern? What do you think, Nolan?
I don't think so, because it has to be subtracted.
It's supposed to be subtraction. Okay, then next question. Can g of x be rewritten in a way that it does fit the pattern with subtraction? Yeah?
Just do x minus 1.
X minus minus 1. Yep. So we can use the remainder theorem to do h of x divided by g of x. What is the number that we're going to plug in for x this time? Yeah? Negative 1, exactly. It's the number after the minus sign. All right, so let's plug negative 1 in and see what happens. So we get negative 1 cubed minus 2 times negative 1 squared minus 1 minus 5. So that gives me negative 1 minus 2 minus 1 minus 5. And what does that come out to? Yep,
-9.
negative 9. Okay, so that's my remainder when I do f of x over g of x. Okay, I got a remainder of negative 9. What does that mean about g of x? Because the remainder wasn't 0. It means what? Yeah.
It's not a factor.
That's not a factor either. So if you're trying to factor f of x, these are not factors that you would use. Yeah.
So when you're like dividing, because like g of x, you switch the sign out with the sign and then the opposite of the constant?
Well, in this one we had to, yeah. Because when you're doing the remainder theorem, it's got to be x minus, and then you need to take what's in that box and plug it into the numerator. So if you have x plus, that's not the right set. So that's why we switched it. All right, let's try this one. Okay, in the book, you're going to see something about using the factor theorem. I just want you to use the remainder theorem. It's kind of the same thing. But just use the remainder theorem. How would you use the remainder theorem to show that that is or is not a factor of that? What do we have to do? Yeah, Kelsey?
Would you plug -2 in for x and see if there's a remainder?
Okay, and how do you interpret the remainder?
So if it's 0, then it would be a factor.
Okay, and if not,
It's not a factor.
then it's not. So think of that x plus 2, that's what you're dividing by, but you got to think of it like this. So she correctly said plug in -2 for x in the numerator. That's the numerator. And see what you get. -2 cubed plus 5 times -2 squared. And then I simplified a little bit. What's -2 cubed? Yeah, no. -8. 5 times -2 squared, that's 4 times 5 is 20. Minus 10 minus 2. What's -8 plus 20? About count. 12. And 12 minus 10 gives me 2, and then minus 2 more? 0. So we got a remainder of 0. So what does that mean? Yep,
It is a factor.
that is a factor. Okay, so that means if you were trying to take x cubed plus 5x squared plus 5x minus 2 and factor it, x plus 2 is a factor. How would you get the other factor? Yeah.
You divide x plus 2.
What would you do?
Divide x to the third plus 5x squared plus 5x minus 2 by x plus 2.
Yes. And when you divide it out, you'd be looking for the quotient. So this is the other factor. It's your quotient. Okay, we're not going to divide it out and do it, but if you did, that's how you would factor that cubic, knowing that x plus 2 is a factor. And when you get your quotient, the degree on this factor is a 1. What would be the degree on your quotient? Because if you distributed it to this factor, it has to come out to a cubic. What would be the degree on my quotient? Yeah?
Squared.
Yeah, this would have to be a quadratic, because a quadratic times a linear gives you a cubic. Okay, any questions on that? All right, so last thing. So we've been looking at different statements. I use statements like roots, zeros, factors. All those things I'm saying are they're really the same idea. So if you have a number that you can plug in to an equation and it comes out to 0, that number is called a 0. That number is also called a root. Okay? But I want you to look at something else. I had this quadratic earlier, something like, I think it was 5x plus 6. And I wrote it as x plus 3, x plus 2. What number could you plug into the first factor to get 0? Yeah. -3. And the second factor? -2. So knowing the factors allows you to figure out the roots. But it also works the other way. Let's say that I said you've got a polynomial and 4 is a root and -2 is a root. If 4 is a root, what would be the factor that it came from to give you that? Yep.
-4.
X minus 4. And if -2 is a root, what would be the factor that it came from?
X plus 2.
X plus 2. So if you know the root and you do x minus that, that number is a factor. So if you know a root and you write x minus that, that is the factor. And how do you know it's a factor? Well, fill in c right there. C minus c gives you 0. If you plug it in, you get 0. Okay, so that's going to be important for the next problem, because I'm going to give you some roots, and I'm going to have you work backwards and tell me the factors. And lastly, if you have a root, what is that number graphically? Like if you made a picture of your equation, the root is where your graph does what?
Intercepts the x-axis.
Yeah, where it crosses the x-axis. Okay, so getting kind of a connection between all those ideas, that's important. Roots, factors, x-intercepts. They're all kind of the same concept. Okay, so I want you to find a polynomial that has degree 3, and the roots of it are -2, 1, and 3. So your first step is to take each one of these roots and convert them into what they would be as a factor. Okay, factor means it has like an x minus or an x plus. And we'll have to FOIL it all out. So -2 is one of your roots. What would be the factor that came from? Linear factor. Yep.
X plus 2.
X plus 2. What would be the linear factor that 1 comes from? Yep.
X minus 1.
X minus 1. And the linear factor that 3 comes from? X minus 3. So once we FOIL that out, that should give us the answer we're looking for. Okay, so we get x squared minus x plus 2x minus 2. And now we need to FOIL that with x minus 3. So we get x cubed, x squared, -2x, and then we get -3x squared, minus 3x, plus 6. All right, let's see what we get. X cubed. We have an x squared and a -3x squared. So that's going to be -2x squared. -2x and -3x is -5x. And plus 6. All right, let's check it. So if we type that in, it should cross the x-axis at exactly the 3 numbers up above, -2, 1, and 3. Okay, so we got x cubed minus 2x squared minus 5x plus 6. Okay. And does that look like it crosses the x-axis at -2, 1, and 3? Yeah. I mean, isn't that cool? I mean, you can make a polynomial that crosses at any number you want. It's like amazing. You could somebody could be like, oh, I bet you can't. You go, no, I can. So it's just, yeah, you just do that. It's pretty cool. All right, any questions on that? All right. So now the last thing is same concept, but I want to take this and I want to get back to that. So I want to take something that's been all multiplied out and change it back to the factors so I can get the roots. Now, in general, that would not be an easy thing to do, but the question that I'm giving you is going to have a trick where it ends up working out nice. So we're going to try to use factor by grouping on this. So factor by grouping is when you have 4 terms, and the first 2 and the last 2 have something in common. And you hope that things work out nice. If this didn't factor by grouping, then what I would do is I would type that in on the calculator and do second calc 0. We talked about finding zeros on the calculator before? Okay. That's what I would have to do if this didn't factor. But it does. What do these first two terms have in common that I could factor out of them? Yeah.
X squared.
Yep. So factor out an x squared. And what does that leave me with inside parentheses? Yeah.
X plus 2.
X plus 2. Now the goal with factor by grouping is you need to get an x plus 2 again in another set of parentheses. So we just have to hope that that happens. If it doesn't, you go to the calculator. What do these two terms have in common? Negative 4x and negative 8. Yep.
Negative 2.
Even bigger than negative 2.
Negative 4.
Yeah, we can go negative 4. And what would that leave you with inside the parentheses if you take negative 4 out? Yeah?
X plus 2.
That leaves you with an x plus 2. Now we know this is going to work out nice. Okay, look at that term and look at that term. What do both of those things underlined in red have in common now that I can factor out? Yeah?
X plus 2.
Yeah, we're going to take the x plus 2 out. If you take x plus 2 out of the first term, what's the only thing that's left? X, yeah,
Squared.
x squared. And if you factor the x plus 2 out of the second term, what's left? Yeah,
Negative 4.
negative 4. Okay, so we're almost there. At this step, we're basically where we were at this step. Now we've got a quadratic and we've got a linear. We want to get a linear, linear, linear. We want to get 3 linear factors. Okay, so we've got x plus 2 and x squared minus 4, that's a difference of 2 squares. So that'll factor again. How does x squared minus 4 factor? Yeah.
X plus 2, X minus 2.
Yep, x plus 2, x minus 2. Now we've got 3 linear factors and we can write the roots. Or the zeros, but it said zeros, same thing. What would you plug into this first factor to get 0? Yeah,
Negative 2.
negative 2. What would you plug into the second factor to get 0? Yeah, negative 2 again, you don't need to write it twice. And what would you plug into the third factor? Yeah?
2.
2. So the fact that we got negative 2 twice means this is what we call a repeated root. Okay, negative 2 is a repeated root. So that means it would look something like this. It would come up, we'd just barely touch negative 2, and then go like that. But that graph looks something like that. When a cubic just comes and touches the axis and bounces away, that's usually a hint that one of the answers is a repeated root because you got the same factor twice. Yeah.
When you write like the repeated root thing, can't you do like the plus or minus sign in front of it?
So in this one, you could write plus or minus 2, but the roots won't always be symmetrical. Yeah. Okay, so there are 3 answers to this problem. Don't think that technically there are 3. Negative 2, negative 2, and positive 2. It's just the 3 answers aren't all unique. So that's 3-3. Okay, so that's the homework for tonight on 171. We will go over that tomorrow, and then we will finish up our material for the week with synthetic division tomorrow, which is a faster way of doing long division, but it only works in special cases, kind of like the remainder theorem. It's a very specific case that it'll work in. Friday we have our test. Progress report's closed Friday, so I'll be doing your grades based on what I have as of once you finish the test. And I'll be after school on Thursday for extra help. Yes?
You want to